Hello, this first video will be about a presentation of the three-dimensional soil module in FEM-Design. So I will talk about the main features and practical examples. So here you can see the contents. First of all, I will talk about the development of the three-dimensional soil module. Then I will talk about some theoretical background of the nonlinear calculation of the soil. Then I will show you the main features of the new FEM-Design version about three-dimensional soil module. And then at the end I will show you a practical example. So this is a PowerPoint presentation. And in the second video of this three-dimensional soil, I will show you some practical example in live in a program. So first of all, some word about the development. So there are problems where the classical mechanical calculations failed, such as we cannot use the truss element, the beam element, or the plane stress or plane strain element for modeling a three-dimensional solid element. So in the ancient times, the reason was to use these models to reduce the number of equations. So there were several approximations to model the reality. But for example, in this case, when we talk about a three-dimensional soil or the calculation of three-dimensional soil problem, it's obvious that in some cases this approximation cannot be applied. So furthermore, the capacity of the computers is continuously increasing. So we developed this module because the solid problem, the soil problem, is especially a three-dimensional problem. So we cannot avoid and approximate this three-dimensional behavior with different mechanical models. So as you know, almost in every case, the soil and the foundation are parts of the complete structure, buildings or roads equally, and there will be some soil and structure interaction between them. So in reality, most of the soil behaves in a nonlinear way, so that was the main reason why we developed the material model in nonlinear way. And obviously, as I mentioned earlier, a three-dimensional soil problem is a three-dimensional solid problem. So you can see here some theoretical background and the connection between the strain field and stress field. You can see here the figures in 3 dimension for a three-dimensional block. You can see here the stresses and the strains, and as we know, there is a material model where we can find which show us the connection between the strains and between the stresses. And as I mentioned earlier, in the new FEM-Design module there is a linear material and 2 different nonlinear material for the calculation of the soil. So when we're talking about nonlinearity in the soil, there are several new material properties which affect the final behavior of the soil. So in a linear case, the Young's modulus and the shear modulus affects the deformation and the stresses in the soil. And if we are talking about an isotropic material, the Poisson ratio is not independent from E and G. But when we are talking about the nonlinearity of the soil, the effective friction angle, the effective cohesion, or the unraised shear strength, and the mean effective stress level are also very important variables, because these variables affect the final settlements and the stresses in the soil. So first of all, I would like to talk about the three-dimensional solid elements in FEM-Design. So in FEM-Design there are 2 different element group: the standard, the linear shape functional elements, and the quadratic shape functions elements. So in the three-dimensional model for the three-dimensional solid elements, there are 4 different element types. First of all, we have the tetrahedron in a linear with the linear shape function and with the quadratic shape function. And we have also the pyramid element, the wedge element, and the hexahedral elements. You can see here the different node numbers and the different element types on the right side. So by the calculation we use these types of elements. So just a summary about the theoretical background. You can see here the global equation system of the structure. The K is the global structural stiffness matrix, the V is the nodal displacement, so the V is the displacement vector, and on the right side we have the load vector. So with the geometric equation we can calculate the strain matrix based on the finite element discretization, and we can calculate the element stiffness matrix with this equation. And in this equation, the D matrix is the material stiffness matrix, which affects the final calculation. So we calculate this element stiffness matrix, but for a numerical calculation we cannot able to solve this integration in an analytical way, so we use numerical integration. So it's a summation based on this equation. And if we are talking about nonlinearity of the soil, we need to solve the main equation system several times because we solve the problem in load increments. So when we finish the calculation based on the first load step, then we evaluate the stresses, and based on those stress values in the soil we can update and calculate a new material stiffness matrix based on the nonlinearity of the soil. Therefore we need to solve the problem and the equation system several times because it is a nonlinear material model for the soil, because we would like to follow the nonlinearity of the soil. So you can see here that the nonlinear behavior of the soil depends on the stress state, as I said before, and the stresses, the internal forces, are the slave variables, the secondary variables in finite element method. So according to this fact, when we calculate when we make a calculation with quadratic fine elements, the quadratic fine elements could give more accurate results than with the linear shape function elements, because with the quadratic fine elements we can get the secondary variable stress values in a more accurate way. So during the calculation and during the stiffness matrix calculation of the elements, we need to check the stress state in the integration points of the solid elements. So it is a very important thing that the calculation according to the numerical integration is based on the stress state in the integration points of the solid elements. So you can see here the main features in the geomodel. So first of all, we needed to solve the problem of the automatic three-dimensional mesh generating. So it's very important when we have an arbitrary shaped soil block under the structure, we need to have an automatic three-dimensional mesh generator. It's a very difficult mathematical problem, so it was a very big development in the program. So the second main feature, as I mentioned earlier, the nonlinear material models for the soil. So besides of the linear material model, we have the classical Mohr Coulomb plasticity in FEM-Design, and a stress-dependent elasticity is also available. It's another nonlinearity in FEM-Design. And the third and the fourth main feature is the consideration of the earth pressure on basement walls or any other walls. And the other very important thing is the consideration of the effective stresses. So we consider during the calculation, based on the groundwater level, just the effective stresses in the material model, because the connection between the stresses and between the strain is the material model. But for in soil we need to consider in the stress vector just the effective stresses. So we can subtract the effect of water and subtract the water pressure from the total pressure in the soil. For further details of the theoretical background and the calculation method, you can download a theory manual and verification example for the 3D soil from this link, and you can find several benchmark problems and the complete theoretical background, the detailed theoretical background of the soil calculation method in FEM-Design. So first of all, we solved the problem of the automatic 3D mesh generator. So first of all, we need to apply to make a continuous connection with other elements. So if you have a soil block and there are several plates bar in this block, we need a continuous connection between the nodes if we would like to make a three-dimensional mesh generator. So it was a big mathematical problem, a very difficult mathematical problem to solve this three-dimensional mesh problem. And also, if we have a structure in the soil and we would like to analyze the settlements in an accurate way, we need to apply, for example, a local refinement around the structure, because the soil block around the structure, very close to the structure, has more effect on the final settlement than in a further part of the soil block. So there is an option to have a local refinement around the building or on the structure in the program. So if we would like to make some connection between the other elements, between the connected elements of the soil, we can use different connection elements in the modeling tools part of FEM-Design. So I can set some connections, a line connection, point connection, or a surface connection in FEM-Design also, and it's available for soil also. And we can draw almost arbitrary shape hull space, and we can set arbitrary initial and final ground level of the soil. These levels are important by the nonlinear elastic, stress dependent elastic material model of the soil. So let's talk about again the nonlinear material models for soil. So FEM-Design can handle two types of nonlinearity. The first nonlinear material model is the Mohr Coulomb failure and the Mohr Coulomb plasticity. It's typical for sands or maybe rocks, and the plasticity is applied here, and the elastic properties are stress independent. The second nonlinearity is the stress dependent elastic behavior. This behavior is typical for clays and silts, and in this case the elastic properties are stress dependent, so we modified the compression modulus, or with another word, or with another input, the elastic modulus during the nonlinear calculation. And we can mix these two types of nonlinearity. We can apply the Mohr Coulomb failure by the stress dependent elastic behavior also. So the first nonlinearity is the Mohr Coulomb plasticity, the classical Mohr Coulomb failure criteria. In this case we can set the parameters for Mohr Coulomb plasticity. So in the blue box there is the elastic parameter, the Young modulus, and the Poisson's ratio. We consider an isotropic behavior of the material of the soil, but we need to give strength parameters also, because the Mohr Coulomb failure criteria depends on these strength parameters. The undrained shear strength or the effective cohesion and effective friction angle depends on if we set the undrained or the drained behavior of the soil during the calculation. So during the calculation, as I mentioned earlier, we consider the classical Mohr Coulomb plasticity. You can see here the failure surface in a three-dimensional stress space, and you can see here this is the tension sign and this is the compression sign, and if we are inside this cone, the behavior is elastic, and if we reach the surface of this failure criteria, we reached the end of the elastic behavior and we reached the plastic behavior. So we solve it in different load steps. So for example, in the former load step we have the sigma A value in point A. Then in the next load step we have a delta sigma with a predictor, with a linear predictor. Then we have a state in the B point in sigma B, but this point is outside of the cone, so it's an impossible state. So therefore we need to apply a returning map to the failure surface. So in FEM-Design we're considering associated flow rule. So the plastic potential and the flow surface is the same function in FEM-Design. In this case, the material stiffness matrix and based on this material stiffness matrix, the global stiffness matrix will be symmetric also in FEM-Design. So the other nonlinearity is the stress-dependent elasticity, for example for soft clays, and based on this material model we can consider the nonlinearity, the stress-dependent elasticity of the over-consolidated soil. So for cohesive soil, the nonlinear calculation can be performed regard to soil condition based on laboratory test, where the pre-consolidation pressure and the compression properties are evaluated. And in this case, as I mentioned earlier, the initial ground level and the final ground level affects the final settlement, because if we have this curve where this axis is the stresses and you can see here the strains, so if we have this diagram where these values are the stresses and on the vertical axis we have the compression modulus, we have dropped down when we reach the pre-consolidation pressure in the soil. So after the pre-consolidation pressure, the soil behaves more soft, and before the level of the pre-consolidation pressure, the compression modulus is much higher. So for this stress-dependent elasticity, we need to set several other elastic properties. So we need to give this idealized diagram where the vertical axis is the compression modulus and the horizontal axis is the stress levels in the soil. We can set these initial compression modulus before the pre-consolidation pressure, then we need to give different parameters of this curve to get an idealized diagram of this stress-dependent elasticity in the soil. But also, if I would like to apply the Mohr Coulomb criteria for this material model, we can give the strength parameter of the soil such by the Mohr Coulomb material models. So the stress-dependent elasticity is a very tricky nonlinearity. So we solve the problem in different phases. So first of all, in phase 0, we set the original initial ground level of the soil together with the corresponding initial water level. Based on different sets of soil layers and soil properties, we can calculate the effective vertical stresses, from which the original mean effective stress, the original stress state of the soil, can be calculated. So with this value we can set where are we on this diagram. So the P0 value is calculated based on the initial ground level. In phase 1 we can set the final ground level for the soil. In this phase we also set the structure in the excavation or in embankment. So according to the calculated stresses in phase 0, during load step calculation, the elements integration work with the unloading modulus. It means that until we reach the P0 original value, practically we do not have settlements, because the MUL is much higher than the initial compression modulus value. So after the specific load step we reach the P0 value, and then the elements works with M0 value until we reach the pre-consolidation pressure. So after this PC mean effective stresses, the elements work with the ML value here. So first of all, we set in phase 1 where are we in this diagram, so we get the P0 value, and in phase 1 we calculate the self-stress state of the soil based on the self-weight of the soil and based on the final ground level. So if we have an embankment, it works with the compression modulus above the P0 value, but if we have an excavation, the soils behaves with the Young's modulus, with the compression modulus below the P0 value. So in phase 2 there is the consideration of the external loads. So in phase 2 we consider the remaining loads such as self-weight of the structure, external load and so on. So if in phase 1 there were excavation or embankments, again phase 0, at the beginning of phase 2 calculation solid elements have initial stresses due to phase 1 as I mentioned earlier. And these values depends on the phase 0 and phase 1 as well. During load step calculation in phase 2 we consider stress dependency in the elements according to initial stresses from phase 1 and the input parameters for the soil layer also. Then, so in phase 2 we consider the external loads on the structure, and based on phase 0 and phase 1 the stresses in the soils are in an initial stress state, so we can now just moving on this curve based on the external loads of the structure. So the final settlements calculation are based on this stress dependent elasticity of the soil. So you can see here some benchmark problems. So I will show you in the second video some live problems in the program. So I will show you different models. How can we consider? How can FEM-Design consider the main features of the solid, of the new solid, 3D solid or new 3D soil feature? So now you can see here the consideration of the earth pressure and the effective stresses. So if we have a building, we set different groundwater levels. We have different earth pressures and water pressures, so final pressures on the basement walls. So you can see here we can check the plastic points in the soil based on the integration points, and we can calculate automatically the earth pressure on retaining walls and so on and so on. So in the second video I will show you some simple practical example about the settlement calculation, about the consideration of the effect of the groundwater level, and the calculation of the pressures on basement walls, and some slope stability problems. So here just a few figures about the settlement calculation based on the Mohr Coulomb criteria. So it's just a shallow wall foundation, and I just modeled the half of the problem here. So I used the symmetry plane here and applied the load at the top of the soil, and we set a linearly varying cohesion and a linearly varying compression modulus, or with another setting we can set a linearly varying compression modulus and elastic modulus in the program. So it's not independent from each other, of course. And if we increase the load at the top of the soil after before some amount of load values, the behavior is almost linear. Then based on the plastic behavior we reach the load bearing capacity of this shallow foundation, and we have endless settlements at the certain amount of load levels. So in this case, by this problem, the friction angle was 0, so it was a cohesive soil. So you can see here under the shallow foundation the plastic points in the soil block. So in this example it was a frictional soil with a very low cohesion, and in this case this is just an isolated circular foundation. I modeled just a quarter of the model. We use two symmetry plane here, and you can see the local refinement in the mesh. And if I increase the loads here, the behavior is obviously nonlinear, and a certain amount of load level, of course, we reach the load bearing capacity of this circular isolated foundation. You can see here the verification of the soft clay model, the stress dependent elasticity model. So if I apply an idealized diagram and we set and we apply a certain amount of load at the top of the soil block, and if we increase this load, we have the following behavior. So before the pre-consolidation pressure the soil behaves with a larger compression modulus, then it drops down and the behavior is very soft. Then we have a hardening part at the end of this calculation. With this Young's modulus, with elastic modulus, are these hardening part of this idealized compression modulus stress diagram based on this diagram. And as I mentioned earlier, we can consider the effect of groundwater level also. So if we set different groundwater levels, the settlements and of course the reaction forces at the side walls of the soil block will be different, because the effective horizontal pressure and the water pressure also different if we have different load levels in the soil. So you can see here the vertical stresses and of course the effective vertical stresses and the effective horizontal stresses based on the different groundwater level in the soil. And of course this lateral pressure is different on the basement walls if we have different groundwater levels. So if we set different groundwater levels, the resultant pressure on the walls based on the lateral effective earth pressure and based on the lateral water pressure will be different. So the design of the basement walls is solved in FEM-Design also based on the different groundwater level and based on the different soil properties. So based on the different groundwater level, we can have different bending moment distribution in the foundation slab and in the wall, the basement wall of the structure. You can see here some picture, some figure about the slope stability problem. So if we have this type of slope and we apply a load here, we can calculate the stability of the slope. If this slope is stable with the adjusted material parameters, we have finite amount of displacement. But if we have an unstable slope, we have large deformation under the self-weight or under the external loads. So we can consider and realize that there will be a slip surface in the slope. You can see here the slip surface here. But in the next video I will show you some live example in the program about this very small practical examples. And finally you can see here a cantilever wall with different soil level on the right side and on the left side. You can see here the mesh, and here we have a cantilever wall, and we can calculate the bending moment diagram and the connection forces, which means the active and passive earth pressure on this wall. You can see here the plastic points also, and I will show you in the next video that we get very different solution when we calculated this problem, for example, or other nonlinear problem with linear way or nonlinear way. So when we have a nonlinear calculation, the program can consider automatically the passive and the active earth pressure on the different side of the wall, and based on this earth pressure, based on the Mohr Coulomb failure criteria, Mohr Coulomb material model, we can calculate the right bending moment diagram and shear forces on the cantilever wall, and we can get quite a different solution for this bending moment diagram if the calculation is linear. So the linear material model is not appropriate to modeling such a problem like a slope stability or a cantilever wall. And I guess this was my last example, so thank you for your attention. And in the second video you can find live example in the program about how the program works and how can we calculate the different nonlinearity in the program.